Welcome to another Ultralight Airplane Design video from the Ultralight Airplane Workshop. In this video, we're going to continue the series that we've started on the UWS-4 Ultralight Airplane. And if you aren't familiar with what an ultralight airplane is in the United States, let me just briefly mention what that is. It can only carry one person. The power off stall speed cannot be more than 24 knots, and that's around 28 miles per hour. The empty weight of the airplane cannot be more than 254 pounds. And the requirement that's going to be really important for this video is the maximum power, maximum speed of the airplane in level flight cannot be more than 55 knots, and that's around 63 miles per hour. If you're not familiar with the series that we're doing here on the design of the UWS-4 Ultralight Airplane, I'll put a link here in the upper right hand corner that you can go to, and that will be a playlist for all the videos that we've done so far on this airplane. Now in this series, we're using a book from Dan Raymer called Simplified Aircraft Design for Homebuilders to help guide us in this design. In this video, we're continuing on with our work on Chapter 7 called Analyze It. And this is the second section in Chapter 7 where we're going to work on propulsion. Now in a previous video, and I'll put a link up here in the upper right hand corner, we did some engine sizing. So getting a rough idea of the diameter of our prop, the RPM of our prop, and the size of our engine, in other words, the horsepower of the engine. But that was a pretty limited analysis. What we're going to do here is go back and do a slightly more in-depth analysis of what we need for our horsepower and for our propeller. And speaking of Dan's book, we're going to mention something here that we've mentioned in just about every video that we did on this ultralight airplane. The videos I'm doing here are not really a substitution for Dan's book. We're not using everything that Dan has in his book. But if you think you might be interested in an airplane design and not necessarily an ultralight airplane design, Dan's book is intended for light airplanes like home-built experimentals, then I think it'd be a good idea for you to check out Dan's book. Like the title says, it is pretty simplified. And by the way, there's a link down in the description that will take you to a page on the Ultralight Airplane Workshop's webpage that has a list of books that I'm interested in, that I like, and one of those links is for Dan's book. That will take you to Amazon. If you use that link to buy the book, the Ultralight Airplane Workshop will get a small cut of the proceeds of the sale of that book. Another thing I like to do right here at the beginning of the video is review what we learned in the last video. Frequently that's used in this video, and sometimes it's just good to kind of refresh our memory of what we did. In that video, it's the first section on reanalyzing our design. We worked on some of the aerodynamic characteristics of our plane, kind of reevaluating some of those things, getting better numbers. So we worked on the coefficient for parasitic drag, and we worked on the induced drag factor. The last thing we worked on was the maximum coefficient of lift of the wing, both with and without flaps. Now for this video, it's important to review what we did in the last video because we're actually going to use those drag factors in this video. Now in Dan's book on this section where we're talking about propulsion, there's kind of an implicit assumption that you're going to pick your engine based on maybe an engine you already have, or an engine that you can afford to pay the fuel consumption on, or maybe just buy flat out, or you're going to pick the biggest engine that you can fit onto the airframe based on how much the airframe can take on weight and balance, or how much torque it can handle. And once you get that engine, you're just going to live with whatever that maximum speed is that you can get out of it. Now you may pitch the propeller for that maximum speed, or it's possible, depending on what the mission of the airplane is, you'll actually pitch the propeller for fantastic climb and give up some of your maximum speed. So that's kind of the implicit assumption that's based in there. Now you could try to assume that for ultralights too, but we have a design requirement that the FAA is sticking on us that kind of restricts us a little bit. So here's the thing that gives us a little bit of problem with following that assumption that we just talked about in Dan's book. And it's this one right here. The maximum speed of our ultralight cannot exceed 55 knots, about 63 miles per hour. And by the way, what I'm going to talk about here is from the FAA Advisory Circular 103-7. This advisory circular does a much better job of listing and explaining the regulations for Part 103 than Part 103 itself does. So we're going to be using this advisory circular here in this video. So in Chapter 20 of this advisory circular, it basically reiterates what's in Part 103, We cannot exceed 55 knots in level flight. This isn't a speed limit like on a highway, where your vehicle can easily go over what the posted speed limit is, and you are voluntarily, if you do it, adhere to that speed limit. The FAA really isn't fond of voluntary compliance with the regulations. They want the airplane designed so it is physically not possible for that airplane to go over 55 knots at maximum power in straight, steady, level flight. Now, if the FAA happens to be somewhere where you are flying or someone reports you for going more than the specified 55 knots, it's possible that they will pay you a little visit and you will have to demonstrate that your airplane does not go over 55 knots in straight and level flight. Now, one way to do that is to use Appendix 1 of Advisory Circular 107-3. And we'll get to that a little bit more later. We're actually going to use that in part of our design here. Another way to do it is to do a timed run over a course. And this advisory circular talks a little bit more about the details of doing that. Or you could also do a radar gun test. Now, if you want to do the time speed or the radar gun, I'd recommend go ahead and doing that ahead of time and have some paperwork that shows that you did this so that you don't have to go and demonstrate it for the FAA. You can show that you've already done it and have some paperwork shows that your plane doesn't go over 55 knots. Of course, that doesn't really mean that they won't ask you to do it again so they can see it personally. Now, there are several methods you can use to meet that 55 knot limit speed. Now, one way is to restrict the amount of power your engine can produce. For example, you could put a stop on the throttle cable up near the carburetor. Now, one thing that you'll see here in this advisory circular is that any artificial means that you use to restrict power, it can't be accessible by the pilot while the airplane's flying. So somewhere up near the carburetor where the pilot can't reach, that would be reasonable. But if it's some sort of little lock nut that's on the throttle where the pilot could reach it and modify it, that would not be acceptable. But of course, restricting power for your airplane can bring some undesirable characteristics. For example, your climb speed could be terrible. Your climb rate could be terrible. So you'd have to do some analysis to decide if that would be desirable or not. Another way to do it is to use a less efficient prop, or to do a speed reduction on the prop so it runs at a much lower RPM. That would be possible too. Or you could add some aerodynamic device that adds drag. So it could be something like an automatic speed brake that deploys as you start getting close to 55 knots. It would have to be automatic and can't be modifiable by the pilot again. Or you could add something like a big fat strut or something that adds more drag to the airplane. So that would be advantageous to still get you fairly good climb because you're going slower when you're climbing, so you wouldn't have as much drag, but it would help restrict your maximum cruise speed because you'd be going faster at the cruise speed, producing more drag. Now, I mentioned using Appendix 1 of the Advisory Circular to figure out what the maximum drag of your airplane is, and by matching the thrust of your motor to the drag that you calculate here, you can still meet Part 103. So let's go through that process here on Appendix 1 on the UWS-4 and see what we get. So the first thing is we're going to come up with a total drag factor for the airplane. So they've broken it down into several parts of the airplane. So the first one is the drag of the pilot. So they have totally exposed, partially exposed, and totally enclosed. And you get different drag factors depending on which situation you have. So we're going to have a streamlined fuselage, hopefully, on the UWS-4, and we're going to be totally enclosed. So that would be a drag factor of 1.5 according to this appendix. Then we figure out the wing drag factor. Now it's a little bit strange here. They're only interested in the horizontal lifting surfaces, excluding control devices. So if you had a canard, it would include the canard, excluding the elevator. And on a wing, it includes the regular part of the wing, excluding ailerons. Now, they didn't mention flaps, but I think flaps should also be included there. So for us, we had 121 square feet for our reference surface area. Our ailerons and flaps cover the whole trailing edge of the wing, and they take up 25% of the chord. So what we want to do is multiply by 75% by our 121, and then they have a multiplication factor that ends up giving you the drag factor out here. So we have almost 1, so a 0.9. So now we go back and add in the control surfaces and stabilizers. So that would be our tail surface area, our ailerons on the main wing, and the flaps. And then we multiply that by this 0.014 factor. And when we do that, we get 0.8. So if you have flying wires, there's a factor for that. We do not have any flying wires on this airplane. If you have struts, for example, wing struts or struts for the tail, we don't have that, so it's 0 for us. They also do landing gear. Now, it's a little bit odd. They don't treat tail wheels or main wheels differently. Now, we have 2 tail wheels and 2 main wheels, so that's going to be 4 wheels for us. And then you multiply the number of wheels by 1/2, and so our result is 2. They have engine drag, and they have different categories for the engine, kind of like they did for the pilot. So you have engine fully exposed, you have engine partially exposed or fairly faired. There were 3 categories there. And so for some components, exposed is 0.5. I think we'll go ahead and use that. Now you subtotal everything that we got so far, and we got 5.7. Now we want to add in a factor for induced drag. The way they do it is they take the subtotal that we just did and multiply it by 0.2, and that gives us 1.14. Now we add up our subtotal and the induced drag, and we get almost a 7, 6.85. So that's the drag factor they want us to come up with. So now we're going to use that drag factor that we had, plus the horsepower of our engine, to come up with what our level flight cruise speed would be. Now, we've been talking about using a 35 horse engine. They don't really ask you anything about your propeller, so I'm not sure what assumptions they're using here. I'm sure we could figure it out, but I don't think it's really worth the effort to do that. So down here on this horizontal axis is our horsepower. Over here on the vertical axis is going to be our maximum airspeed, and these contour lines along here is our drag factor. So you come down here to our 35 horsepower. Let me do a little drawing on the screen here. Now let's come across horizontally. We hit 65 knots. Well, the requirement is that we can't go more than 55 knots. So according to the FAA's little appendix here, we have too much power or not enough drag in order to meet the requirement. Well, I kind of hate to add more drag to this airplane because one of the missions on this airplane is to have as much endurance as I can and have as much range as I can so I can go visit local airports. I had not intended this airplane to be a low and slow kind of recreational airplane. I wanted to use this specific airplane to go a little bit farther. Let's work backwards. Let's assume the 55 knots, come over to our current drag factor, and then come down and see how much horsepower we would need to meet the requirements here. Right here is our drag factor, so let's come over there. And then let's come down. Do a terrible job drawing a straight line. So that's 22 horsepower. So if we had a 22 horsepower engine, and using this calculation that came up for the drag factor, if the FAA stopped us and said, hey, we think you're going more than 55 knots, you can show them the calculations that you came up with, show them your horsepower, and since we would meet the criteria here, they'd have to say, okay, you met the requirements here of this appendix, so you're okay to go. So in that case, we don't have to do the speed test. Now, that doesn't mean that specific FAA representative wouldn't require you to still do some speed test, but you can at least show that you've met their requirements here in this appendix, and that should be good enough. Now, the problem is that's going to require me to buy a new engine. Now, that's kind of cool, though, that it only takes 22 horsepower according to this appendix, because that means I'd have a lower fuel consumption, I would have more range and more flying time, so that's kind of neat. But this appendix is doing a lot of assumptions on that drag factor. My guess is that we would have more drag than this appendix is coming up with. So I think our level flight speed at 22 horsepower would probably be less than 55 knots. So the way they came up with the drag factor in this chart they're using, it has a whole lot of assumptions. It's not very precise. So maybe there's another way we can get more precise numbers. Maybe. Let's give that some thought. Let's see if we can come up with another way of calculating drag at 55 knots. Now, I already have a prop that I had intended to use. Let's see if we can figure out the propeller properties at 55 knots. And then based on that and the 35 horsepower engine I intend to use, let's see if that mix will work or if we're going to have to do something different. So what I want to do is, with the prop I have and the engine I have, what is the thrust at 55 knots? Let's find out what the drag is at 55 knots. And what we want to do is have the thrust be less than or equal to the drag. If we do that, then we'll meet the requirements for Part 103. All right, let's work on the drag first, just like we did on the appendix. So our drag is going to be parasitic drag plus our lift drag, the drag due to lift. So the way we calculate our parasitic drag is we use Q, dynamic pressure. We've talked about that in an aerodynamic terminology video before. I'll put a link to that up here in the upper right-hand corner. We want the surface reference area. We already said that was 121 square feet. And we want the coefficient of drag. And we just came up with that in the last video. And then we want the induced drag. That's a similar equation. Again, we have the dynamic pressure, the surface reference area, and the coefficient of induced drag. Now the coefficient of induced drag is that K factor that we came up with in the last video, multiplied by the coefficient of lift squared. Now the coefficient of lift equation should look fairly familiar. It's the weight divided by the quantity of the dynamic pressure multiplied by the reference surface area. Now the weight I'm going to use is 474 pounds. That's excluding parachute and with the standard weight pilot, and 5 gallons of fuel. As I said, surface reference area is 121 square feet. The dynamic pressure is at 55 knots. And if I remember right, that's just a little bit more than 10 at 55 knots. And that's also using standard atmosphere. So this drag curve should look a little bit familiar to a lot of you. I did this on a spreadsheet. So at various speeds, I got the induced drag. That's this line here, this red line. I also got the parasitic drag, that's this blue line, and then I added the two together, and that's this yellow drag. So what we want to do is know what the total drag is at 55 knots. So that is right here. Well, that turns out to be 52.5 pounds of drag. So what we want to do is have the thrust of our propeller be less than or equal to 52.5 pounds. Now, I already happen to have an UltraProp 1. So let's talk a little bit about the characteristics of this prop. It's a 3-bladed prop. The diameter is 59 inches. The radius of the hub is about 3.36 inches. The chord of the blade right there at the hub is 3.9 inches, almost 4 inches. At the tip, of course, the radius is 29.5 inches. The chord at the tip is 1.97 inches. And this blade is a little bit unusual. It's a constant pitch along the whole blade. Now that's something that can actually be changed with pitch blocks. You can replace some blocks that are there at the hub and change the pitch of the blade. So it's kind of neat that you can do that. And then down here, this is roughly the shape of the airfoil at the root. The tip is very similar, so I decided not to show that too. And by the way, I use calipers to measure the thickness of the airfoil at various X/C, in other words, positions along the chord, and came up with this on my own. Now, estimating performance of a propeller that you don't have performance charts on is a little bit tough. I couldn't find any performance charts here for the UltraProp 1. And in the past, I've always had trouble doing performance estimations on propellers that I didn't have performance charts on. And I stumbled across this program called JBlade. Now, I've only used it once so far, and I'm not completely positive I used it the right way. So in this video, I'm not actually going to go through showing you how I use JBlade. Now in the future, once I'm more confident using the program, I'll probably go ahead and do that. One thing that's kind of neat about JBlade is a portion of it comes directly from the XFLR5 airfoil analysis program that we've used before in this series and a previous series. So at least that part I'm familiar with using. But it also has some extra stuff that's specifically for propeller blades and propellers. So you enter the dimensions of the blade, the airfoil of the blade, the number of blades you have. Then you can run an analysis for various air densities, various RPMs. Then what the program comes out with is thrust at various speeds based on whatever input you put in on RPM, etc. That's what we're looking at here. So down here on the horizontal axis, this is speed. And keep in mind here what we're looking at is in metric units. So this is meters per second down here on the horizontal axis. Up here on the thrust axis, this is in newtons. So 55 knots is around 28.3 meters per second roughly. So that's where this dot is here. That's really close to 55 knots. And by the way, this green slope is when I have the blade pitched at 10 degrees. This blue one you can't see very well down here is at 9 degrees. There's another one up here you can only see the corner of is at 12 degrees. Now I already had done a back calculation using that 52 pounds of drag and converted that to newtons and tried to figure out which one of these various pitch angles came pretty close to matching up with the correct speed for 55 knots. And that was this 10-degree pitch. So this blue line did not give us enough thrust at 55 knots. Yellow line up here gave us too much thrust at 55 knots. And the green line came pretty darn close to what I wanted. So thrust we're getting from the propeller. Oh, and by the way, the propeller RPM that I had was 2,500 RPM. So the thrust we got at 2,500 RPM for the blade pitched at 10 degrees at 55 knots was 288 newtons. So that's what we've got here. Now, when we took our 52 pounds of drag and converted it to newtons, that's 233. So 288 versus 233. So we're getting just a little more thrust from the propeller than our 52 pounds of drag. By the way, that 288 newtons was 64, almost 65 pounds of thrust. Now, let's talk about something that Dan does talk about in his book. He talks about engine drag. He did not include engine drag, cooling drag, in his drag calculations. The way he deals with engine cooling drag is he removes that from thrust. Now, in Dan's book, he talked about several different levels of cooling drag, depending on if the engine's fully exposed or you have nice smooth ducting. And so what I chose is something kind of in between the worst drag and kind of the middle drag, because I think we're going to have a little more drag than I would like for cooling drag. So I picked 13%. So what Dan does is he takes propeller thrust and removes the cooling drag from that. So 88 newtons, removing 13% of that gives us 250 newtons. So now we can actually better compare our thrust of 250 newtons to the 52 pounds or 233 newtons. So now our thrust is much closer to our expected drag of 233 newtons. So that's about 10% more. Now, I'm pretty comfortable with that. The reason for that is I think we're probably going to have more drag than we estimated. That's 233 newtons. Whenever you do drag calculations, it seems like the drag of the airplane to the real airplane is almost always more than the estimate. So I would not be surprised if we come up with significantly more than 233 newtons for the real drag of the airplane. So I'm going to assume this is actually a pretty good number. So now let's figure out how much power we're going to need from the engine to get this 250 newtons of thrust. Well, power turns out to be thrust times speed. So we take our 288 newtons, multiply our speed at 55 knots of 28.3 meters per second. That gives us 8,150 watts, which is about 11 horsepower. Now that's horsepower being basically delivered to the air by the propeller. That's not engine horsepower because our propeller is not efficient. It's not 100% efficient. So we're going to be losing power between the engine power going through that shaft into the propeller and then being delivered to the air. We're losing power in the propeller. Now another thing that JBlade comes up with then is trying to figure out engine power you're going to need in order to go the speed that you want. So this is another graph from JBlade. So again, we're down here at our roughly 28.3 meters per second. So let's come over here and look at power, and power is in watts. So this is saying we're needing roughly 15,000 watts in order to go this 55 knots that we want to do. Well, how many horsepower is 15,000 watts? That's about 20 horsepower. Now from the Advisory Circular 103-7 Appendix 1, we came up with 22 horsepower at 55 knots. And our slightly more rigorous calculation came up with 22 horsepower. And so that's only, 10% different from what that Appendix 1 came up with. So they're pretty close to agreeing. I'm pretty impressed about that. And since we're here, let's figure out what our prop efficiency is. So power delivered to the air divided by the horsepower of the engine, that gives us about a 50% prop efficiency. So assuming that we haven't made a monster mistake somewhere, and I don't think we have, since we've got agreement between our two methods of calculating the engine horsepower. We're going to need engines somewhere between 20 to 22 horsepower. Now, at the very end of this section in Dan's book, he does a calculation to try to come up with thrust. Now, he's assuming that you already know what the efficiency of your prop is going to be. Well, we just calculated efficiency, so let's go ahead and plug this into Dan's equation, and let's see what we come up with for thrust. So here's our horsepower, here's the efficiency we just came up with for the prop, here's our cruise speed, that's going to be at 55 knots. So we plug in our 55 knots, but we have to convert it to feet per second, so that's almost 93. So our horsepower, for the engine horsepower, is 20 horsepower. Now remember, the drag we think we're going to get at 55 knots is 52.5 pounds of force. So let's plug in our numbers here, and we get 59, almost 60 pounds of force. So that's saying that we're probably going to get more thrust than we want, and it'll push us over our 55 knots. So it sounds like the 35 horsepower engine I would like to use is way more horsepower than I need. I really don't, at this moment, want to spend more money on a new engine, a smaller engine. So my initial testing, at least the high-speed taxi testing, I'm going to go ahead and do with my 35 horse engine. Now there's some things I can do to reduce the thrust of this engine. We already talked about some of the things. For example, putting a stop on the throttle cable up at the carburetor so I can't produce as much power as I'd like. I'm not fond of that idea. Another thing that I can do, which is pretty cool about this initial UltraProp, it has lines out on the tips where you can actually reduce the diameter. You can cut the tip off and reduce the diameter of the blade, and they have nice lines there, so you can cut right up to that line and not significantly mess with the balance of the blade. And they're roughly half-inch increments for about 4 inches or so. So I can reduce the diameter of the blade to reduce thrust. And then I don't know if they made 9-degree pitch blocks for this blade. If they did, I'll see if I can get some 9-degree pitch blocks, and that will also reduce the thrust of this blade. Now, reducing the pitch is going to make this airplane a climbing beast. But to really get good cruise efficiency for this airplane, ultimately I do need, I believe, a smaller engine. Might be able to get by with something like a 25, 27 horse engine. And I really do need to get a propeller blade that is more efficient. Now there's currently an UltraProp 2 blade, which is ground pitch adjustable, which I really like also. So I'm probably also going to replace the propeller on this airplane too. Let's talk about what the next video is going to be. That's a third section here in the same chapter on Analyze It, and we're going to start on some preliminary structural sizing. So what we're going to have to do this is we need to come up with some aerodynamic forces on the airplane, the landing forces on the airplane, the forces for deploying the parachute, and we're going to have to start designing some of the structural members for the airplane. Well guys, thanks for watching. Until next time.